Okay, I'm going to start my today's session, uh, and I am going to discuss the correlation between two random variables from a different perspective. There is a special type of correlation coefficient between, often considered in between two random variables. That correlation will be discussed in today's class, and the name of the correlation is as follows. It is called rank correlation. So I'm going to discuss this rank correlation in this session. Sometimes it is also known as Spearman's rank correlation. Okay, so let us try to understand first of all, what is it actually? Let us suppose that a group of n individuals is arranged in order of merit. So we have a group of individuals where number of individual present over there is small n. Okay, according to their merit or proficiency in possession of two characteristics. Okay, so we are arranging this particular group containing n small n number of individuals on the basis of two characteristics. Suppose this is characteristic A and this is characteristic B. What sort of characteristic I am talking about here? For example, just for understanding from the pedagogical point of view, suppose this characteristic is the marks of those individuals in an exam of maths and marks of those in the same individuals in the exam of stat. So these are the characteristics on the basis of which we have arranged the group of individual with respect to their proficiency and their merit. Okay, now the proficiency or merit that we are talking about will place the individuals with respect to the ranks they have got on this individual, on the basis of these individual characteristics. That means a particular individual, say individual number 10, if suppose he has got mark 70 in mathematics, suppose his performance in statistics is poor, he has scored 55. So obviously, if I arrange the individuals according to their rank, so obviously the rank of the individual in these two examination will be different. Suppose the individual 10, I'm calling this individual as 10. This 10th individual has got rank 5 in mathematics, but in statistics, suppose his rank is 7. So the ranks obtained by the individual in the characteristic A and the ranks obtained by the individual in the characteristic B will be different from one another. For simplicity, we are assuming that for simplicity and for the time being, we are assuming that no two individuals are having the same rank. So this is, we are assuming for the sake of our calculation. Okay, later we can modify this, we can generalize this section, and we'll try to see what happens if the two ranks are same. So in this manner, we are arranging the group of individuals according to their rank. And only one thing that remains common in this particular tabulation is that the number of individuals 1, 2, 3 up to n, that doesn't change actually. The number of individuals remain fixed. Just like if I'm concerned about CSE section A, I want to check, I want to place the students of CSE section A according to the ranks they have achieved in a certain examination, in two different examinations. And I hope, I expect that all the individuals, 60 individuals have got ranks, and no two ranks of the two individuals are same. This doesn't happen because of, you know very well why does, this is very ideal case and why doesn't happen actually. But for the sake of the calculation, we are assuming that this is the ideal scenario. So we are considering, we are naming these ranks, we are arranging these individuals as per the ranks. And suppose the ranks obtained by the individuals with respect to the characteristic A is denoted by the random variable X, and ranks obtained by the same individuals with respect to the characteristic B is denoted by Y, capital Y. And these are the different values of the individuals with respect to the ranks given. This X1, X2, X3 or Xn that I'm writing over here, these are actually ranks. And these ranks, these values of X1s and these values of Xi's and Yj's, they will vary from 1 to up to n, isn't it? So what is this X3? This X3, it can be any number between the any number from the set of natural first n natural numbers. Suppose this X3 is if my small n is, say, I'm considering the small n value is, say, 100, then this X3 can be 99. This Y2 can be 92. This Y3 can be 5, anything. So when I'm writing that X3 is 99 and Y3 is 5, that means with respect to the characteristic A, the individual 3 has been ranked 99, and with respect to the characteristic B, the same individual 3 has been placed at the 5th position. So in this manner, we have arranged these individuals as per their ranks. Now, the correlation, if I want to calculate the correlation between these two variables, this correlation coefficient is actually known as Spearman's rank correlation coefficient. And that Spearman's rank correlation coefficient can be deduced from the correlation coefficient that we have already studied. The correlation coefficient that we have studied is going by the formula covariance of xy by sigma x sigma y. Remember that this formula is due to Carl Pearson, and sometimes it is known as Carl Pearson's correlation coefficient formula. So this is the base formula on the basis of which the entire subject of correlation and regression is dependent. Now, the Spearman's rank correlation formula that I'm going to deduce, for that I'm going to take the help of this Carl Pearsonian correlation coefficient to find an expression for the Spearman's rank correlation coefficient. So I'm beginning this particular analysis, and let's see which particular formula we can obtain from this ideal situation. So I'm writing here, I'm going to start writing from the next page, because in this page I have done a sort of rough work. And since I'm going to derive the Spearman's rank correlation formula from Carl Pearson's correlation coefficient formula, so let me start from a fresh page. Now, the derivation. Okay, so assuming that no two individuals are having the same rank, or you can say are not bracketed equal in their classification with respect to the characteristic A and B, each of the variables capital X and Y will range from the values 1 to up to n that I have already explained. I'm going to calculate the mean of these set of values first of all. So first of all, I'm going to calculate the mean with respect to the random variable X bar. And you know that that would be nothing but equal to 1 plus 2 plus 3 plus dot 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 plus n divided by the total number of individual. And this is an AP series, arithmetic progression series. And its formula is n into n plus 1 by 2. And 1n is present over here. So we get the mean of the random variable X, which are actually the ranks, is as n plus 1 by 2. And not only this, you can also check that the mean of the random variable Y is also the same thing, same as mean of X, because this random variable Y also takes values from 1 to up to n. So X bar and Y bar, they are actually same. So we have calculated the average mean rank of the individuals. Next, that is required to calculate the correlation coefficient is the sigma X square, which is the variance of the random variable capital X or variance of rank capital X. And this is given by the formula 1 by n summation I goes from 1 to n xi squared minus x bar squared. Remember that actually the sample variance formula is going by the is written in the following manner. Actually, we divide it by 1 by n minus 1. But for the sake of simplicity and calculation, I am not using this particular formula right now. I am going to use the usual formula of variance, which is often used. When we divide this quantity by n, that is also a kind of variance, but that variance, if I say, for example, if I write the variance formula as this, so the difference between these two expression is that in one expression, we are dividing by 1 by n minus 1, and in another expression, we are dividing by n. So both these expressions are actually calculating the variance, but this is the best estimate of population variance, and this is not the best estimate of population variance. But we are actually not here to study the estimation theory, so we are using the original formula, which is going by the following form that I have written over here. Now we'll do the calculation. So summation xi squared can be written as 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared. And you have already calculated x bar square, x bar. So we are going to substitute this as follows. So x bar is n plus 1 by 2, which is whole squared. Now you know that this is also a kind of arithmetic progression, but its formula is going by the rule n into n plus 1 into twice n plus 1 by 6. Okay, and we are getting here n plus 1 whole square by 4. Okay, so we are getting 1 by n into n plus 1 into twice n plus 1 by 6 minus n plus 1 whole square by 4. This n and that n will cancel each other. So ultimately we are getting n plus 1 into twice n plus 1 by 6 minus n plus 1 whole square by 4. We are now going to simplify this a little bit, and let's see what expression comes out of it. So we'll write 2n square plus, okay, you can do one thing for simplicity. You can take n plus 1 common. So I'm going to take n plus 1 common from this, and then we get twice n plus 1 minus n minus 1. No, let us write it in this manner. If I take n plus 1 common, we are going to get twice n plus 1 by 6 minus n plus 1 by 4. And then I'm going to take the LCM from here. So the LCM is 12. So we get 2 into twice n plus 1 minus 3 into n plus 1. And that is equal to n plus 1 by 12, 4n square plus 2 minus 3n minus 3 by 12. Oh, so 12 has already been written. No problem. Okay, just check the calculation. If I'm doing anything, any mistake, that just point me out. I'm rechecking my calculation once again. So I'm writing here summation xi squared is written as 1 squared plus 2 squared plus 3 squared plus n squared, and this is minus n plus 1 by 2 whole square. So this expression is n into n plus 1 into twice n plus 1 by 6. This n and that n will cancel one another. We are getting n plus 1 n plus 1 into twice n plus 1 by 6 minus n plus 1 whole square by 4. And 4n. From where are you getting 4n? Which one? Which part you are saying? Where is the mistake? Four n. Oh, acha, acha. Yes, yes, yes. Okay, I got your point. That's why I was checking. Now, yeah. So we get n plus 1 into twice n plus 1 by 6 minus n plus 1 whole square by 4. And that is, we are taking n plus 1 common. We are getting twice n plus 1 by 6 minus n plus 1 by 4. So LCM is 12, and we get this expression. So in the numerator, we are getting 2 into twice n plus 1 minus 3 into n plus 1. And from there, we are getting this expression, 4n plus 2 minus 3n minus 3. So that is equal to n plus 1 into n minus 1 by 12. Okay. And this expression is nothing but equal to n square minus 1 by 12. Similar calculation will also reveal that this expression of sigma x squared is similar to the expression of sigma y square also. So if you calculate sigma y square, you will get the same expression as sigma x squared. So we have calculated x bar and y bar. We have also calculated sigma x squared and sigma y squared. Now I'm going to the next page. Now you see that in general, according to our assumption, this xi and the yi, they are not same for all I, because the ranks are different. So since they are not same, we assume that capital Di be the deviation between the ranks xi and yi for the ith individual. So Di is given by xi minus yi. How the 2 points x, how the 2 ranks are deviated from one another. This deviation can also be written as follows. We can write it as xi minus x bar and yi minus x bar. Because you see, if I remove the bracket, minus x bar will cancel plus x bar, and xi minus yi will remain as it is. But we know from our previous page that x bar and y bar, these two items are same. So we can write this deviation as xi minus x bar minus yi minus y bar. Okay. Now we are going to take the square of the deviation, and then we are going to calculate the sum of the square of the deviation. When deviation, if we take the sum of the deviations only, there is a high probability that we can get 0. Then there will not be there will be no justification in calculating the rank correlation, because if the deviation comes out to be 0, covariance can also come out to be 0. Okay, so to analyze the thing, we always have to take the sum of the squares of the deviations. Now therefore we are squaring this left hand side, and we are taking the summation. The summation is running from 1 to up to n. The same thing will be done on the right hand side. So I'm going to write it like this: xi minus x bar minus yi minus y bar, this whole square. Now I'm going to break the square, and you know this a minus b whole square, s square plus b square minus 2ab. So if I break it in this manner and operate the summation on individual terms, we are going to get like this: summation over I xi minus x bar whole square plus summation over I yi minus y bar whole square minus twice summation over I xi minus x bar into yi minus y bar. Next, we are going to divide both the sides by 1 by n. So we get 1 by n summation I goes from 1 to n di squared, that is equal to 1 by n summation I goes from 1 to n xi minus x bar whole squared plus 1 by n summation yi minus y bar whole squared, I goes from 1 to up to n, minus twice 1 by n summation I goes from 1 to n xi minus x bar into yi minus y bar. So we are getting 1 by n summation di square I goes from 1 to up to n is equal to, try to identify this expression. This expression is nothing but the variance of x. So for this expression, we can write 1 by n summation xi minus x bar whole square. This is variance of x. So we can write sigma x square plus 1 by n summation I goes from 1 to n yi minus y bar whole square is sigma y square. And try to identify this expression 1 by n summation I goes from 1 to n xi minus x bar into yi minus y bar. This is covariance of xy preceded by multiplied by the constant quantity 2. So we are actually getting this expression. Just carefully observe. For the expression covariance of xy, let us use a symbol now. Okay, let the symbol for covariance of xy be, suppose the covariance of xy is given by the symbol rho xy. Okay, just for simplicity, I am doing this, because in otherwise each time we have to write it covariance xy. So I'm denoting this covariance xy by the symbol rho xy. So we are writing it in this manner: sigma x square plus sigma y square minus okay, not this symbol will not, it would be much better if I write something. I'm going to change this thing a little bit. Let us not name this covariance xy by any symbol. Rather, what we can do is that we can do one thing. We know from our previous knowledge that the correlation coefficient rxy is given by the formula covariance of xy by sigma x into sigma y. So we can express covariance of xy in terms of correlation coefficient. But since capital R, this symbol is retained for Karl Pearson correlation coefficient. And since in this particular section, we are actually calculating a special case of Karl Pearson that is known as Spearman's rank correlation coefficient. So we can denote this correlation coefficient by a quantity, a symbol which we can call as rho xy. So we can call it as rho xy. So rho xy is the correlation coefficient, but we are changing the symbol for the time being, since we are interested in a special case of Karl Pearson correlation. Because if you write the correlation coefficient Rxy, so this can become a little bit confused, because we are right now we are not calculating we are not deriving the Karl Pearson correlation, we are deriving the Spearman's rank correlation. So that's why I'm changing the symbol. So you see that covariance of xy now can be written as, we can express this covariance xy by rho xy. Okay, I'm writing rho xy in this manner, rho xy into sigma x sigma y. Now we can substitute this particular item over here, rho xy into sigma x into sigma y. So we have got our 1 by n summation di square as this. But also in the previous page, we have also obtained, and we obtained already that sigma x squared, the expression of sigma x squared and sigma y squared, they are also same according to our current situation. So we can replace all the sigma y's by sigma x. So we are writing it as 1 by n summation di squared, I goes from 1 to n, sigma x squared plus sigma y squared. So in place of sigma y, we are writing sigma x squared minus rho xy into sigma x into sigma x. Okay. Now let us further simplify it. What we can do is that we can write it as 1 by n summation I goes from 1 to n di squared is equal to twice sigma x squared minus, oh, one thing I have missed, one term called 2 was there, so I'm writing the 2, the constant 2 over here, that was missing, and I'm putting the 2 in this case also. So we are getting from these two expressions, we are getting sigma x squared plus sigma x squared as 2 sigma x squared, and this is written as 2 rho xy sigma x squared. Take 2 common, and we can write it as, oh, you can take we can take 2 sigma x squared common. So we can write it as 2 sigma x squared 1 minus rho xy, which is equal to 1 by n summation di squared. So this implies 1 minus rho xy, which is 1 by n 2 sigma x squared summation I goes from 1 to n di squared. Okay, and you can write it as, you can keep rho xy on the left hand side, and you can take the other quantities on the right hand side. So we get summation I goes from 1 to n di squared by, oh, I do not have place over here, so I'm writing in the next page. So we can keep rho xy on the left hand side, and we can take the rest of the items on the right hand side. So we get 1 minus I goes from 1 to n di squared divided by twice n sigma x squared. And you can substitute the form of sigma x squared in the formula also. Sigma x squared came out to be n square minus 1 by 12. That was also equal to sigma y squared. So we can substitute that. So we get 1 minus summation di square. I goes from 1 to n, divided by twice n into n square minus 1 by 12. And you have to simplify this quantity. So 2 will cancel 12 and we'll get 6. 6. And from this expression, we are ultimately getting rho xy to be 1 minus 6 into summation di squared by n into n square minus 1. This is also a correlation. You can say that is Karl Pearson correlation coefficient is different from this. The answer is no. Karl Pearson's correlation coefficient is not different from this. They are actually same. Karl Pearson's correlation coefficient, the rho xy is actually rxy. They are not different. But I am changing the symbol just to let you know that when we consider rxy, that is Karl Pearson's correlation coefficient, we actually mean that we are considering two variables of any type. These two variables, capital X and capital Y, constituting the bivariate distribution, will be of any types. Okay, we are not concerned about what type of variables they are. But when we are talking about the Spearman's rank correlation, then you have to keep in mind that these two random variables, capital X and capital Y, they must be ranks and no other different things. Okay, you cannot consider, you cannot say that I have marks of X and marks of Y. I want to calculate the correlation coefficient between the two marks. That will not be Spearman's rank correlation coefficient. If you want to calculate the Spearman's rank correlation coefficient, then you have, based upon the marks, you have to place the individuals in terms of their ranks in the two sets, and then you can correlate the ranks, not their marks. So correlation between the marks and correlation between the ranks, these two things are different actually. So therefore, the correlation between the marks means it is saying that if we have a group of individuals, how the marks of maths and marks of stats are moving together. That means if I see that marks of maths is increasing, if I plot it as a scatter diagram, on the x-axis, say I'm putting maths marks, on the y-axis I'm putting stat marks, and if I'm seeing that, okay, the tendency is in increasing direction, we will conclude that if individual's mark is greater in maths, then it is supposed to be, it is quite obvious that the individual will be good in stat also. So his maths mark is increasing, his stat mark is also increasing. So maths and stats are positively correlated. So for stat, a particular person has to have some basic knowledge about maths, or the person has to be good in maths. That is the conclusion that we can draw from calculating the Karl Pearson correlation coefficient between the two marks. But if I arrange the individual with respect to their marks, with respect to their ranks, and if I try to find out the ranks of the individuals, the correlation coefficient between the ranks, that means what we are doing actually. The individual perform, right now I am not concerned about maths and stat, I am concerned about the individual himself. The individual is concerned. I am trying to look at the individual from two different perspectives. Okay, so when I'm trying to correlate the left-hand side column with the right-hand side column, that means same individual is taken into consideration and his ranks are being correlated. So these two situations are actually different. And just to distinguish between the two correlation coefficient, I have actually use two different symbols. So from now onwards, we will try to use any other symbol other than RXY to denote the Spearman's rank correlation coefficient. You can select rho, or you can select any symbol, any Greek letter that you are fond of to denote the Spearman's rank correlation, but just do not use Karl Pearson's symbol. Try to distinguish between the two. Although Karl Pearson is a special case of this one. And this formula that we have obtained, remember this quantity, which is actually a number, it is 6. So whenever a particular set will be given to us, we will first try to arrange the individuals with respect to their ranks. Once we arrange the individuals in ranks, so what we'll do, if suppose the values of x, y, and yi, xi and yi are given, so first of all, according to the information given, we will arrange them according to their ranks. We'll assume that no two individuals are having the same rank, and since in the formula di square, summation di square is there, so we will first calculate di by subtracting one from the other. You can do it yi minus xi also, because in both the cases, some of the deviations will be positive, the other will be negative. But always remember that sum of deviation is always equal to 0. Sum of the deviation is always equal to 0. Why it is so? Because if I am writing summation I goes from 1 to n di, that means what? I goes from 1 to n xi minus yi. Okay, that means summation I goes from 1 to n xi minus summation I goes from 1 to n yi. And we know that this is nx bar and this is ny bar. But we know also that x bar equal to y bar. So nx bar minus nx bar is obtained, and which is equal to 0. Therefore, after calculating this, we'll try to find out di square, and from there we'll calculate the summation of that. We will put the values and we'll calculate the rank correlation coefficient. We are going to look at a few examples in the next session. Those examples will be discussed with respect to Spearman's rank correlation coefficient.